Your ancestors that it turned into like.
Maybe they'll, be worse than.
Section 5, Newton's law of gravity. So we come back to Newton. He has another law. It's about gravity. Every object in the universe attracts every other object with a force that has the following properties.
Wait, so there's 4 laws?
Well, so this was about gravity. So the force is inversely proportional to the square of the distance between the objects. Inversely proportional means 1 over, and then the square. So something is being squared. What is it? The distance. So that will be called radius. Okay. So the force between the two. So we have force. Okay. And the force that's interacting between the two would be the force of one on the other. So 1 on 2, or vice versa, 2 on 1. Okay, and then the other part of this is the force is directly proportional to the product of the masses of the two objects. So the mass of the first one we could call M1, and the mass of the other we could call M2. So now I don't need this 1 up here. I have M1 times M2, the product of the two masses. Okay, so that's basically what these two parts are saying here. Now, instead of a 1, we probably have some sort of a constant there, okay? So I would put a K for constant.
But that's still over R squared, right?
Still over R squared. So these are the two parts of Newton's law of gravity. Now, down here, we can see what Newton's law of gravity is. It just doesn't have the letter K. It has a capital G. So we just have to learn what that capital G is, and basically we have already written what Newton's law of gravity is, okay?
Gravity's older brother.
Gravity's older brother, yeah, that's right. So if two objects with masses m1 and m2 are a distance r apart, then the objects exert attractive forces, basically gravity, on each other of the magnitude f1 on 2 equals f2 on 1. So those are action-reaction pairs. Capital G, m1, m2 over r squared. The forces are directed along the line joining the two objects. The constant G is called the gravitational constant. And with SI units, the gravitational constant is 6.67 times 10 to the negative 11th power, and that's Newton meters squared divided by kilograms squared. That block of units right there is set so that the units work out when you do all the multiplication and dividing. Okay? It's not like some, being came down and told us that that's what they were. They just set those units up so that they divide out and multiply out nicely when you do all the multiplication and dividing. Up top here, we have kilograms times kilograms. So that's why we're dividing by kilograms here, squared. And on bottom, we have meters and meters. So meters squared. And that's why on top we have meters squared. So those units are all gone. And since we're talking about a force here, we have to wind up with newtons. And that's why there's newtons sitting right here. That's why the units are the way they are. Okay? So anyway, 6.67 times 10 to the 11th, negative 11th power. You got to remember that one. That's an important one. You're going to be using it quite a bit. And that's Newton's law of gravity. So we're going to move on.
How come it's such a small number?
Because the gravitational attraction between two bodies is incredibly tiny. When you're dealing with
the weakest forces.
When you're dealing with a massively large body like a planet, the mass takes over and accounts for all of the attraction. If you had two small bodies, like two people standing next to each other, or a desk and a chair or something like that, the mass of those two objects is so small that that gravitational constant really doesn't do anything.
So you're telling me we're meant to gravitate towards me? At a very
Because you're so massive? Yeah, no, that's not it. Okay, so a little review of inverse square relationships. So two quantities have an inverse square relationship if y is inversely proportional to the square of x. So we have y on the left side, and we have x squared on the bottom on the right side. So what does this look like if we have a graph? So here, a is just a constant, so that will be like your capital G, the gravitational constant on top. The relationship is sometimes written as this symbol right here. That's like an infinity symbol that's just not closed, okay? That's a proportional, inversely proportional relationship symbol. So basically what happens, if I double the x, okay, so I'm doubling the denominator that's being squared, what happens? The y value will decrease by the square of that number, okay? If I have x, then because I'm having the denominator, I'm going to square that and I will increase the y by a factor of that value squared. The reciprocal of that value squared basically is what happens. So since I have x, I take the reciprocal and I square it. So that means I will increase the other by a factor of 4. So if I increase x by a factor of 3, take the reciprocal and then square it. So 1/3 squared is 1/9. I'm going to decrease y by a factor of 9. Okay. If I decrease x by a factor of 3, so that's like 1/3. Take the reciprocal of that, I get 3. Square it, I get 9. I'm going to increase y by a factor of 9. Okay? So generally, when I increase x by a factor, y is going to decrease by that factor squared. If I decrease x, I'm going to increase y by that factor squared. Okay? That's the inverse.
Like the last chapter with.
Yeah. Okay. So the graph over here shows that pretty nice. So if I take the x, so the x is sitting right here, I'm going to increase x by a factor of 3 right here. Maybe I'll make it 4. Then I'm going to decrease the y by a factor of 1/4. If the x is sitting right here and I increase, decrease x by a factor of 1/2, then I will increase y by a factor of 4. Okay, so that's how that works. Okay, so of course we also have the mass relationship on top. If I increase one of the masses by a factor of 2, then I will also increase y by a factor of 2. So, because that's a directly proportional relationship. Increase one of the masses by a factor, y will increase by that same factor.
But the x has a greater ability to increase. I don't know. Because it's being squared.
No, the radius is being squared. So as the radius increases, the radius is being squared on the bottom, so that has a greater impact.
That's what the x is the radius.
Yeah. Okay. So the gravitational force between two giant lead spheres is 0.010 newtons when the centers of the spheres are 20 meters apart. What is the distance between their centers when the gravitational force between them is 0.160 newtons?
Okay, so when your gravity force increased.
So what we would do here is we have the distance between their centers when the gravitational force between them is this. We had original gravitational force between them here. So take the new gravitational force, 0.160 newtons, divide by the original gravitational force, 0.010 newtons. We're going to get this ratio. This is creating like a scale factor. How much was the gravitational force scaled up? 16 times. Okay, so this is a scale factor of 16 times. All right, this is acting like the y that we were just talking about. I increased y by a factor of 16, which means that x must have been decreased by a factor of 1/16.
Yeah.
Okay, so we had 1/16. Now that means that this factor was really squared. Since we're talking about 16, what squared became 16? 4. Okay, so that means we have a factor of 4 working on 20 meters. So the centers of the spheres were 20 meters apart, in order for me to wind up with this factor of 4 here,
No, divide.
I'm dividing by 4,
To get 5.
so I wind up at 5 meters. Is this going to write? Okay, 5 meters. There we go. All right.
Concepts.
It's a concept, absolutely. The gravity increased, right? So the spheres must have gotten closer. They increased by a factor of 16 with the gravity. Since we had to square, 16 was the number that got squared, so that means 4 was squared. So I must have decreased their distance by a factor of 4. So I took 20 and divided by 4, and I got 5. Okay? Totally a concept problem. All right. Now we have, we're seated in class next to another student, 0.60 meters away. That's pretty standard for like our tables right now. Estimate the magnitude of the gravitational force between you. Assume that you each have a mass of 65 kilograms. So that's around like 140, 150 pounds.
No.
So we need to figure out what
More like 100 kilos.
the gravitational force.
Estimate the magnitude of the gravitational force between you. That means you're looking for F.
Okay.
Okay?
And it's estimation, so we don't have to do that many calculations.
This is an estimation, yeah, but we can do the straight up calculation. So the formula we're using is F equals G M1 M2 over R squared. And this is just straight up plugging in the numbers.
So R squared is 0.6 meters, right?
0.6 meters, yep. Okay, so
9.8 times 65 times
Oh,
65.
it's the thing, the 10 to the 11th, isn't it?
yes, 6.67
That's right.
times 10 to the 11th. And what were the units?
Newtons times meter squared divided by kilogram squared.
Good. Okay,
3.6.
Sorry.
what is it?
No, nothing.
Okay, so we have 65 kilograms.
And then,
Times 65.
That's going to be squared because we have 2 of them, right?
Yep.
And then times,
No, divided.
oh, sorry, yep, it's
Yeah.
divided by.
divided by point.
36 or 3.60. Because that's what 6, no,
0.6 meters.
I'm just going to write it down. So
squared.
kilograms. Oh my God, I'm totally meters. Okay, squared. Okay, and we're just going to type all that into our calculator and get an answer. While you guys are typing that in, we have meter squared on the bottom, meter squared on the top. Those are gone. Kilograms squared on the bottom in the numerator, kilograms squared in the top on the numerator. Those are gone. And I'm left with newtons.
I got 7.82799 times 10 to the negative 7.
Okay, and so significant figures, looks like we have 2 of them. So 7.8
8 times 10 to the negative 7.
10 to the negative 7th newtons. Now, is this a significant number?
No.
It's very
Wait.
0.1234567
7,
8.
Yeah.
Okay, that's a seriously tiny number, newtons. And newtons are not a very big thing anyway, right? So this is not really something that you're going to feel,
So then, like,
unfortunately.
if you weigh, per se, 600 pounds, people are going to gravitate.
It's not even going to really change anything.
It's just crazy for me to think about that. The more you weigh, the more people are going to gravitate towards you. Like,
Okay, yeah, that's true, but it's not really going to change much. All right, so next problem. What is the magnitude of the gravitational force of the Earth on a 60 kilogram person? The Earth has a mass here and the radius here. And remember, we're going to use uppercase letters for the larger mass and radius. What do we do?
okay, that same equation, isn't it? F equals G times
Sure, yeah.
M1, M2. So M1, does it matter which one's which of M1 and M2?
It does.
M1
So
would be the bigger.
the italics here says we're going to use capital G for the gravitational constant, and then big M for the mass of the Earth, little m for the mass of the person, and then over,
R squared.
and then we're going to say big R for the mass, or for the radius of Earth,
So
squared.
how come you're using
$10, this ends up with 9.8 meters a second squared.
So we're using big letters and little letters to represent big objects and little objects,
Okay.
rather than using subscripts. Okay, so we have F equals
6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared times 5.89 times 10 to the 24th
5.98
or 98. That's going to be in kilogram, yeah.
kilograms. Yep,
Then times that by 60 kilograms.
60 kilograms.
Divide it all by the radius of 6.37 times 10 to the 6th.
Meters squared. Okay, now we know the units are going to work out here on the basis of the last problem. So we can type into our calculators. What is the force?
It's got to be hot.
What is your guess again?
9.8.
Well,
Yeah,
it
but
won't be
that's in meters per
9.8.
second squared. We're in newtons.
I'm gonna go
You used to call me on the cell phone.
something around 11.
But it should be just short of 600 because 9.8 is just short of 10. 10 times 60 is 600.
I got 1.87849 times 10 to the 9th.
Definitely not whatever that was.
I don't know what I did wrong there.
I don't either. But do it again. You got to get the right answer. I don't know why you're the only one using a calculator.
6.67
Cole, grab me one. 66.
times 10 to the negative 11th
Mm-hmm.
So Lexi's one. But she's not here, so I can use it.
times 5.98 times 10 to the 24th
Uh-huh.
times 60.
Uh-huh.
That's on top.
Did you forget to square the denominator?
No, I squared it. 6.37 times 10 to the 6th
Uh-huh.
squared. 5.89. I don't know what I did wrong. No, not 5.89. 589.
Oh, 589, that's it?
0.793.
Okay, so we're probably going to call that 590.
Yeah, I got 589.7.
590 newtons. And if we just did our normal calculation where we did mg,
Mass times gravity.
60 times 9.8,
588.
with significant figures, that would take us to 590 also, but a slightly different number, right?
Well,
So how come
Yeah.
you can't use that one?
Slightly different number. With this calculation, we're using an approximate mass of Earth and the gravitational constant and the average radius of Earth. So in the beginning of this course, we remember are using an average gravitational pull of 9.8 meters per second squared. So, and these numbers here that we're using for the radius of Earth and the mass of Earth are going to be a little bit more accurate than the calculation that we're using with the constant of 9.8.
I'm curious to know how they found the mass of Earth.
wait,
Yeah,
quite the trip.
that would be.
So the formula for gravity on the surface of any planet or star, any large object, so satellites like moons and so on, is the gravitational pull of the planet will be the gravitational constant times the mass of the planet divided by r squared of the planet. or star or moon or whatever.
Anytime I see that big GM, I think of GM Motor Company. Just immediately think General Motors.
Oh yeah, okay. Gravity is proportional to the mass of the planet and in an inverse square relationship with the radius of the planet. So this means that the larger the radius of the planet, the less gravity it will have. The larger the mass of the planet, the more gravity it will have. Okay? So if the object is above the surface of the planet or star, then the gravity formula becomes G equals capital G, so the gravitational constant, times the mass of the planet divided by r squared. If you're in a passenger airplane at 10 kilometers, G drops. So we're flying above the surface of the earth. The gravity that you will feel is about 0.3% less than on the ground. So calculate G now for the International Space Station at its orbital height of 400 kilometers.
So we need to change. No, we need to change. No.
We can do
We
a.
gotta change that. We gotta change the stuff to meters.
Well, sure. Okay, so how many meters are we talking about here?
4.0 times 10 to the.
It's 40,000.
This would be 400, and then move the decimal 3 places. 1, 2, 3
400.
meters. 400,000 meters. Okay, so now we're talking about something above the earth, right? So we're going to use G equals the gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times, what is it?
Mass. What's the mass of the Earth?
I don't know. We've seen it several times now.
5.9
times 10 to the 24. Is that going to be another number we're going to need now?
Yep, 5.98 times 10 to the what?
24
24
Yeah.
kilograms.
kg.
All over the radius, which we're gonna have to know that.
Okay, so it's 400,000 meters.
Squared.
Okay, but then also the
Plus-
radius of the Earth. So
Yeah.
plus,
Oh, wow.
what is the radius of the Earth?
6.37. 10 to the 6th.
So times 10 to the 6th. What is that? Times 10
Square.
to the 6th meters. All of that is squared.
So how come you're adding the?
Because this is from the center of the Earth, right? The center of the Earth to the surface of the Earth is 6.37 times 10 to the 6th, but now we're going out beyond that. So we have to add that 400,000 meters to get up to the International Space Station. Okay, and then all of that is being squared. So what is it?
Oh. I thought you meant the whole equation.
Mm. 8.7.
8.7.
0261.
Okay, so we'll write down 8.7. What are the units?
Meters.
Per second squared.
Yeah, meters per second squared. This is gravity out there, right?
How did
So
you get that so fast? Cole?
it's significantly lower.
I used that equation. I
Oh.
just typed it in.
Now we want to calculate the orbital period of the ISS. So how long does it take the International Space Station to go around the planet one time?
So we're trying to find T in this case.
Yep, T equals what?
2 pi, and then square root r over g.
Yes, R over G. So we have 2 pi square root. We need the radius again.
Which is going to be that bottom number. 6. So 4,000 and plus 6
Yep.
point.
400,000
400,000.
meters plus 6.37 times 10 to the sixth.
Squared.
It's not squared. This is just the radius,
Oh, okay.
but it is divided by this new gravity that we just calculated. So whatever the calculator's answer was that you just got, 8.7 is what I'm writing down though.
2.
So we're just gonna get seconds.
This will be in seconds.
Holy crap.
6.37. 10 to the 6. 8.7. Oh, no, that's right.
Some big numbers.
Whoa. 5,541.
5541.78
0.78.
seconds. Let's see if we can get that into minutes.
Divide by 60.
Divide by 60, yeah.
92. So
92 point,
363.
so 92 minutes. And now we have the actual correct orbital period for the International Space Station using the right gravitational pull. So now it's fixed. If you remember back in the last section, we had the wrong one. Now we have the right one.